comet, 3 times farther from the Sun than Earth, appears to breathe. 3. Atlas is exhaling 40 kilograms of water every second in deep cold where comets should sleep. If that sounds impossible, stay with me because this paradox only gets stranger. Start with what we can prove. Ultraviolet eyes in orbit NASA's Swift telescope caught a ghostly halo of hydroxyl surrounding 3 Atlas. Hydroxyl forms when sunlight smashes water apart, so if you see OH, water was there moments ago. Crunch the photons and you get an eye-watering rate, about 1.35 times 10 to the 27th molecules per second, which translates to roughly 40 kilograms per second bleeding into space. At 3.5, 1 astronomical units from the Sunday. That's beyond the orbit of Mars, out where sunlight is a whisper, and most comets are comatose. So what turns a frozen interstellar rock into a faint, distant fountain? Comet physics usually follows a tidy script. As a comet falls inward, sunlight warms the surface ice. Solid turns straight to gas sublimation, blasting through pores and vents, dragging dust with it to build the classic coma and tail. But that engine needs heat. Far from the Sun, water ice is Loctite. Our local comets rarely wake that early. 3. Atlas either missed the memo or writes its own. Let's put the behavior on a simple scale. Double the distance from the Sun, and you get a quarter of the light basic inverse square law. At over 3 AU, the available energy is meager, and yet the signal isn't a trickle. It looks like a system already in second gear, throwing off a small car's worth of water every minute, in a regime we'd call too cold to matter. That's the paradox that hooked astronomers, and that's why telescopes across wavelengths took a number. There are 3 clean possibilities. 1. Our activation thresholds for distant comets are wrong because the microphysics is sneakier than our models. Porous ice, strange textures, and buried volatiles can funnel sunlight where it counts. 2. This object's inventory is different, with super volatile ices or chemical compounds that liberate water indirectly. 3. The data are being misread. But the hydroxyl line is a sturdy proxy, and independent teams saw the same thing. When numbers converge, we listen. You've seen interstellar visitors before. Oumuamua, which refused to behave like any comet we know, and sped away with a nudge we still argue about. 2 Borisov, the opposite, gloriously comety, rich in carbon monoxide, weird but familiar. 3 Atlas slots into its own niche, not dry like Oumuamua, not comfortable like Borisov, active early, green later, and chemically too opinionated. Where it comes from matters, because birthplace writes rules. There's also the colour shift to flag. Images of Atlas started fairly neutral and then drifted into an eerie green as it warmed, a sign that new emitters' cyanide bands, atomic nickel, were lighting up. The brightness didn't just rise smoothly with sunlight. It jumped as if some hidden switch flipped. That switch on behaviour is a clue. It suggests layers, thresholds, and reservoirs turning active on their schedule, not ours. So we're going to do this like a proper investigation. We'll test the energy budget. We'll compare to homegrown comets and ask why this one breaks ranks at distance. We'll examine the spectra for metals that don't usually show, and for volatiles that rewrite the roles of water and carbon dioxide. And we'll keep one eye on the orbit, because trajectory tells origin, and origin explains chemistry. If a comet can look alive without being alive, that's fine by me. It means the physics is dramatic enough to fake a heartbeat. It means the cold between worlds isn't empty, just slow. And it means we might be watching, for the first time, a rulebook drafted around another star bleed into ours line by line. Stay with me. The numbers hold, the mystery deepens, and the next clue is waiting in the green. When the vibes are weird, the numbers are where we start. Hydroxyl is not poetry, it's a receipt. Sunlight hits water, snaps it, and one of the shards is OH. If you can count OH in ultraviolet, you can back out how much water must be breaking apart right now. Do the radiative transfer, apply the fluorescence efficiencies, and you land on a blunt figure for 3 Atlas, roughly 1.35 times 10 to the 27th water molecules per second. Convert from molecules to kilograms, and you're staring at about 40 kilograms every second. Cold space, hot math, no hand-waving. Now line that up against the energy ledger. In basic terms, the Sun's power at a given distance scales with the inverse square. At 3.51 astronomical units, A comet gets barely 8% of the sunlight Earth receives. Take the simple equilibrium temperature rule of thumb, 278 Kelvin, divided by the square root of the distance in AU, and you land near 150 Kelvin. That's under the comfortable activation zone for water ice. In labs and models, water tends to stay quiet at those temperatures. Carbon monoxide and carbon dioxide? Sure, they can party farther out. Water? Not usually. So how is a fountain running where the faucet should be frozen? One answer is geometry. Surfaces aren't flat. They're a maze of pores, cracks, and hollows. Sunlight can get funneled into pits, heat can linger, and pockets of ice can ride localized microclimates that are warmer than the global average. Another answer is that sublimation is a threshold game. For a while, nothing much happens. Then a tiny crack opens, gas vents, the local pressure drops, and suddenly more ice sees vacuum and flashes to vapor. A trickle triggers a cascade. We also need to be honest about proxy chains. We don't see liquid water. We infer water from the OH emission brightness via conversion factors that depend on how efficiently solar photons pump the molecule and how long OH survives before it's destroyed. Those factors have uncertainties, but they're not wild guesses. They're hammered down by decades of comet observations. Multiple instruments can look at different bands and cross-check. When independent analyses land on the same production rate, the needle moves from maybe to pay attention. Context helps. Typical solar system comets wake up in water around 2 astronomical units, sometimes closer. Earlier than that, the show is often driven by carbon monoxide or carbon dioxide, which break free at lower temperatures. That's why distant comets can glow without water lines surging. 3I Atlas complicates the script. We're seeing strong evidence for water-derived OH at a distance where water is normally a wallflower. Either the ice is unusually exposed, the nucleus is unusually dark and heat-absorbing, the porosity is doing acrobatics, or there's chemistry in play that liberates water indirectly. There's a tempting but dangerous escape hatch. Blame the data. Maybe background subtraction trimmed too hard. Maybe the coma model assumed the wrong expansion speed. Maybe the fluorescence efficiencies were off for this radiation field. Fair. We should push the numbers until they either break or refuse to. That's how science keeps itself honest. Yet so far, the rate holds under different assumptions within reasonable error bars. The signal isn't a wisp, it's a loud whisper across a quiet background. Here's where it gets even more interesting. The water story doesn't live in isolation. As 3I Atlas drifted inward, other emission lines, cyanide, atomic nickel started to pop, and the brightness of those bands grew faster than sunlight alone would predict. That superlinear rise hints at switches being flipped, reservoirs being tapped, and distributed sources forming in the coma as tiny icy grains lift off the nucleus and start sublimating on their own. If the coma itself becomes a factory, the energy calculus changes. You don't just heat a surface, you heat a cloud. So, what survives contact with the arithmetic? 1. The hydroxyl detection implies real, sustained water loss at an unfriendly distance. 2. The energy budget is tight but not absurd if microstructure, porosity, and grain lift are doing the heavy lifting. 3. The behavior is inconsistent with run-of-the-mill comets and squarely in pay-attention territory. Numbers don't flinch. They also don't explain themselves. That's our job. Which brings us to color, because the next clue waits in a shade the night sky rarely wears, and once you see it, you can't unsee it. You've seen comets glow before. Dusty white. Maybe a faint blue from ion tails. But 3I Atlas does something that makes astrophotographers rub their eyes. It turns green. Not a shy tint. A vivid, almost neon wash that creeps across the coma and refuses to stay subtle. The night gets a new color, and with it, a new question. What's lighting this lamp? 2 culprits step forward. Cyanide molecules radiating in the green, and atomic nickel singing its own bright line. Neither is shocking in isolation. CN bands are regulars in comet spectra, and nickel atoms can appear when metals are liberated. What is shocking is timing and intensity. As 3I Atlas moved inward, those lines didn't just scale with sunlight. They surged. Superlinear. You expect brightness to follow the inverse square of distance. Half the distance, roughly 4 times the light. Here, the climb outpaces the math, as if flipping a hidden breaker turns on extra bulbs we didn't know were wired. That switch-on behavior is the fingerprint. It says thresholds. Something crossed a temperature line, a pressure line, a structural line, and now new chemistry is allowed. Below the line, quiet. Above the line, party. That's how real materials behave. Ice isn't a perfect slab. It's a maze. Pores, veins, inclusions, cavities. One region stays cold while another sunlit pocket warms just, enough to sublimate a volatile that was locked a moment earlier. Gas percolates, lifts dust, and suddenly a second, distributed engine ignites, the coma itself. Picture tiny icy grains torn from the surface by the first outgassing. They drift, still cold. A few thousand kilometers from home, they soak in more sunlight, each grain its own miniature world. One by one, they cross their personal thresholds and begin to sublimate. Now, the green emitters aren't just attached to the nucleus, they're floating factories, painting the coma from the inside out. That turns the inverse square into a worse than inverse square curve, because you're increasing both illumination and the number of active sources. A feedback loop. A fuse that burns through the cloud. Could the surface alone explain it? Maybe. Thermal fracturing can rip open fresh material. If sunlit and shadowed regions stress the crust, new cracks expose pockets that were insulated. Fresh ice means fresh gas. Fresh gas means more grains liberated. This too feeds the loop, but the color's breadth hints at something beyond a handful of vents. The green spreads wide and fast, consistent with many emitters activating across the coma, not just a single jet carving a streak. Now, about nickel. In most comets, if metals start to show, iron tags along. Here, nickel gets the spotlight and iron stays in the wings, if it shows at all. Combine that with the green intensification, and you get an odd duet, volatile-driven CN plus atomic nickel amplifying in lockstep. That suggests a layered activation. Water-related activity wakes first and tosses grains, then cyanide and nickel sources, likely trapped in different matrices or bound in fragile compounds, cross their threshold and flood the spectrum. The sequence matters because it tells us about the stack of ices and the chemistry of the nursery where 3I Atlas formed. There's an objection worth hearing. Maybe changes in viewing geometry, phase angle, or instrument. Band passes exaggerated the green's rise. Sensible to check, yet multi-instrument detections, different sites, different nights, all saw the same swell. When the effect survives diverse eyes, it's rarely a calibration ghost, so the green isn't a mood. It's a mechanism. It's Atlas revealing that comets can behave like systems with valves and latches, not just passive snowballs. It tells us a switch has flipped, and that switch is probably distributed through a cloud of grains that wakes in waves. And if a comet can do that out in the chill, then small changes in heat can orchestrate big changes in light. Next up, a metal mystery that refuses to travel with its usual partner. Nickel walks on stage alone, and that choice could rewrite a chapter of comet chemistry. Metals in comets are supposed to hunt in pairs. When a nucleus warms enough to liberate atoms, iron and nickel show up together like old friends who always split the check. That's the pattern across our backyard. With 3I Atlas, the pattern breaks. The Very Large Telescope turns its spectrograph toward the coma, and nickel's line blazes bright, while iron is missing in action or barely whispering at the noise floor. It's like seeing footprints without feet. Smoke without fire, nickel without iron, start with what's typical. In solar system comets, iron and nickel cohabit the same mineral phases, condense out of nebular gas at similar temperatures, and with enough heat sublimate together. That's why observers treat their ratio as a sanity check. But at roughly 2.8 astronomical units and beyond, Atlas throws a curveball. Atomic nickel clocks in around a few grams per second, sustained, while iron stubbornly refuses equal billing. If the usual chemistry were running, those iron lines should be obvious. They aren't, so what gives? One road points to fractionation, nature's way of sorting the pantry. Imagine a nursery where nickel got locked into compounds that crack and vaporize at modest temperatures, while iron wound up in tougher, refractory minerals that need far more heat to budge. As Atlas warms, the nickel-bearing phases release atoms into the coma, but iron stays caged in solid grains. The ratio you measure is no longer a window into bulk composition, it's a window into what's easy to free. Another road is organometallic. On Earth, nickel forms volatile complexes like nickel carbonyl when carbon monoxide and the right conditions meet. In a carbon monoxide-rich birth environment, Nickel could have been packaged into fragile molecules that disintegrate under sunlight, spitting out atomic nickel long before iron has any comparable escape route. If that's true, the nickel line isn't telling you more nickel overall, it's telling you easier nickel now. There's a harsher road too, space weathering. Bathe an interstellar object in ultraviolet light and cosmic rays for eons and surfaces change. Bonds break, atoms migrate. You can build a skin, a radiation-sculpted rind where nickel becomes overrepresented or iron becomes chemically locked. When the first warmth arrives, that altered veneer vents into space, biasing what we see. The bulk inside could be perfectly ordinary. The shell could be lying. We should admit the dull possibility. Iron lines might be there, just below the thresholds of our instruments or tangled with other features our current setups don't isolate well. Spectroscopy is a game of signal and subtraction. If a line hides under a brighter neighbor, or the coma's conditions broaden it into invisibility, patience, and better data might make iron reappear. That's why the calendar matters. As Atlas descends toward perihelion, its temperature climbs. If iron ever plans to show, the coming weeks are its chance. Here's the stakes. If iron emerges with warming, the universe breathes a little easier. Nickel first was a trick of timing and chemistry, not a violation of the family rules. If iron stays, missing. If nickel keeps singing solo all the way through perihelion, we're looking at something deeper. Either Atlas formed in a star system with elemental ratios unlike ours, or its chemistry assembled along pathways that our nebula never favored. In both cases, cometary metal emission stops being a footnote and becomes a message. Nickel's loneliness also talks to the green story. Those vivid hues rose with cyanide and nickel lighting up together, suggesting layered activation. Water-related activity kicked loose the first grains. Then, as thresholds were crossed, the sources for CN and nickel switched on. If iron's switch doesn't exist or sits at a temperature, Atlas never reaches that absence is diagnostic. It tells you the architecture of the comet's chemistry has rooms that don't connect. So we watch the lines. We let data decide whether this is a timing gap, a surface trick, or a star-forged signature. Meanwhile, another riddle hums in the background, the gas mix itself. Because if a comet flips the script on metals, wait until you see what it does to the pecking order of volatiles. In most comets, water is the headline act and carbon dioxide is the side guitarist. With 3i Atlas, the billing flips. Some measurements point to a volatile budget, where carbon dioxide does the driving potentially as high as the vast majority of output, while water tags along as a minority player. That's not a cosmetic tweak. It's a rewrite of what we think a comet's engine looks like when the sun is still a dim bulb on the horizon. Why does that matter? Because each volatile has its own comfort zone. Water ice needs relatively higher temperatures to sublimate efficiently. That's why classic water-driven comi roar closer to 2 astronomical units and within. Carbon dioxide and carbon monoxide are the sprinters in cold air. They can leap off the surface far earlier. If Atlas is indeed carbon dioxide forward, then the distant activity that stunned observers suddenly has a natural throttle, a super volatile engaging well before water should wake. But this isn't just a thermostat story. Volatile ratios are a map of birthplace and history. Carbon dioxide condenses at higher temperatures than water, so a comet born slightly closer to its star, yet still beyond the snow lines, might pack proportionally more carbon dioxide if the disk mixed materials in the right way. Planetary migration can stir the pot. Giant planets ploughing through a young disk, sling ices across temperature zones, seeding building blocks with odd inventories. Add irradiation, ultraviolet light, and cosmic rays process ices over millions of years, making and unmaking molecules until the surface chemistry barely resembles the original recipe. Now, fold in the timing we've seen. Water-derived hydroxyl appears surprisingly early. Later, the coma greens as CN and atomic nickel surge. Where does carbon dioxide fit? If carbon dioxide is truly dominant, it may be the backstage crew that lifts icy grains into the coma at distance. Those grains then become roaming factories, later warming enough to release CN, while surface pockets or fragile complexes spit out nickel atoms. The sequence carbon dioxide lofts grains, water registers in OH, cyanide and nickel ignite. As thresholds click threads the observations into one narrative engine. There's a catch. Measuring carbon dioxide from Earth is hard. Our atmosphere drinks those infrared wavelengths. We often infer carbon dioxide via proxy bands, model fits, or space-based windows rather than grabbing a clean spectral license plate. That means uncertainties. Could the carbon dioxide fraction be high but not absurd? Yes. Could it vary with time as active regions rotate in and out of sunlight? Also yes. The safe position is neither denial nor overreach. The balance of evidence leans to a carbon dioxide-rich regime that's unusual by solar system standards. Even if exact percentages move as new data land, suppose the inversion holds. What kind of nursery writes that ratio into stone? A disk with a warmer inner reservoir, feeding icy planetesimals. A star with a radiation field that bakes carbon dioxide chemistry into grains. A system where migrating giants hauled carbon dioxide-rich snow inward to where comets accreted. Or, most enticingly, a birth cloud whose elemental and molecular starting points were simply different. Less iron showing up later aligns with this theme of familiar physics, unfamiliar pantry. And then there's the practical payoff. If carbon dioxide runs the show at distance, our predictions about when and where interstellar comets will flare get better. We stop waiting for water to speak and start listening for the colder voices. Survey strategies change. Filters change. We catch more objects inbound while their comae are still thin, and we won't be surprised when a green veil appears after the initial carbon dioxide-driven lift. A comet dominated by carbon dioxide isn't a violation of nature. It's a clue that nature uses a larger menu than we've sampled at home. 3 interstellar visitors, 3 different chemistries, which raises an obvious question. Is diversity the rule out there? Or did we just meet 3 eccentrics by chance? 3 interstellar visitors in 7 years is not a census, but it is a conversation. Each one arrived with its own accent, its own chemistry, its own way of breaking our expectations. Oumuamua in 2017. 2. I Borisov in 2019. 3. I Atlas now. 3 postcards from elsewhere, and not a single one reads like the others. That's either wild luck, or the first glimpse of a rule we've never written down. Start with the quiet rebel. Oumuamua didn't show the classic coma. No visible dust jets, no obvious gas lines. Yet, as it left the inner solar system, its path curved just a hair more than gravity allowed, as if something were pushing gently from behind. Outgassing without the usual fingerprints was one. Camp's answer. Exotic ices sublimating invisibly was another. Whatever the mechanism, our neat categories wobbled. We had an object that behaved comet-like without looking comet-like. It told us absence of a tail doesn't prove absence of activity. Then came Borisov, a relief to many. At last, a visitor that looked like a comet should. A diffuse coma, a tail, a chemistry we could parse. And yet, even Borisov leaned into the strange, unusually rich in carbon monoxide, a hint that it formed in very cold regions of its natal disk. Familiar silhouette, unfamiliar recipe. Lesson 2. Normal is local. Change the nursery and the baseline shifts. Enter 3. I Atlas, which feels like a compilation of curveballs. Water-derived hydroxyl, at a distance where water should be shy. A late-blooming green cloak driven by cyanide and atomic nickel. Nickel lines bright with iron possibly missing or muted. And a suspected volatile budget where carbon dioxide calls the plays. If Oumuamua challenged what counts as a comet and Borisov challenged where comets can form, Atlas challenges how comets switch on and what elements ride with them when they do. So, is this diversity the point? Maybe our first 3 are not outliers but samples from a distribution we've never measured. Planet-forming disks come in flavors, different stellar types, different metallicities, different radiation fields, different migration histories. It would be surprising if the solids they assemble weren't just as varied. If every star bakes its own pastry, some comets will be buttery with carbon monoxide, some flaky with carbon dioxide, some dry and brittle like Oumuamua. Diversity becomes the rule, and our solar system becomes one dialect among many. Or play devil's advocate, we might have rolled 3 6s in a row. With detection thresholds biased toward the unusual, maybe eccentric objects are easier to notice. A dry, tumbling shard with a weird light curve grabs attention. A textbook visitor hiding in the clutter might slip past surveys. If so, we're currently oversampling the oddballs. The fix is simple but expensive, better, deeper, wider surveys that don't just catch the loud ones. Either way, the strategy changes. If diversity is real, we can no longer treat comet as a single template with minor tweaks. We need branching models, different volatile stacks, different grain physics, different activation thresholds. Predictions become ensemble forecasts, not one-size-fits-all curves. If we're oversampling outliers, then scaling up detections will fill in the middle, showing us the quiet majority we've been missing. There's a subtler implication. Each visitor is not just an object, it's a probe for its home system. Oumuamua may encode surface physics shaped by processing in interstellar space. Borisov whispers about cold formation zones and CO-laden grains. Atlas hints at thick disk chemistry, carbon dioxide forward inventories, and nickel pathways that decouple from iron. 3 messages, 3 signatures, 3 chances to triangulate how star systems write their own chemical biographies. So we keep the conversation going, catch them earlier inbound. Spread the observing net across wavelengths. Archive spectra so future models can reread the lines with fresh eyes. And remember the humility clause. With 3 data points, you can sketch a story, not a conclusion. Still, the emerging story is irresistible. The galaxy doesn't make one kind of comet. It makes many. And if that's true, then every inbound speck of ice is not just a curiosity. It's a chapter from a book we didn't know we could read. Next, we crack open the mechanics that could make such variety look alive. Switches, cracks, and grains that turn a cold rock into a self-amplifying light show. If 3i Atlas looks like it switches on, what's actually flipping the switch? Start with the simplest truth. Comets aren't billiard balls. They're porous, layered, stress-prone, assemblies of ices and dust with voids, veins and glue that fails under even modest heat. When sunlight begins to soak into that mess, small differences in texture turn into big differences in behavior. And sometimes, that behavior looks uncannily like a system choosing to wake. Picture the surface as a patchwork of microclimates. A sun-facing pit traps light like a little oven. The rim stays cooler, the floor warms. At first, it's not enough to free much water. But carbon monoxide or carbon dioxide can slip out through micropassages, lowering pressure in nearby pores. The moment a thin crust fractures, vacuum meets fresh ice and sublimation jumps. Gas rushes through the new vent, drags dust, and crucially tears loose tiny icy grains that escape the surface entirely. That's where the plot twists. Those grains float into the coma as independent worlds. Each has its own size, porosity, and spin. Each heats at its own pace. A kilometer from the nucleus, thousands of them cross their personal thresholds and start to sublimate. Suddenly, the comet isn't a single engine. It's a swarm of engines. Illumination increases as Atlas approaches the sun. Yes, but the number of active emitters also multiplies. That's how you get brightness growth that's steeper than the inverse square rule predicts. You didn't just turn up a dimmer, you switched on more lamps. Gas-dust coupling makes this runaway plausible. As gases stream out, they impart drag on embedded grains. Smaller grains get lofted first, adding optical depth to the coma and providing fresh sublimation surfaces. More gas means more lofted grains. More grains mean more surface area. More surface area means more gas. Feedback loops aren't metaphors here, they're the math. That's why a distant, too-cold object can appear to hesitate and then, abruptly, bloom. Thermal fracturing layers on top. Ice and dust expand differently with heat. Day-night cycles and rotation-force temperature swings. Across the crust, stress builds, microcracks link up, and then a segment fails. When it does, the newly exposed interior has never seen space. It vents with enthusiasm until the local supply thins, or a fallback blanket of dust chokes the opening. These breath-like pulses can look alive on a light curve, even though they're just physics exploiting weak spots. Now add the layered ice stack. Not all ices free themselves at the same temperatures. Carbon monoxide comes first, then carbon dioxide, then water, with organics and metals wrapped into matrices of varying fragility. If 3i Atlas carries strata, CO-rich packets near voids, carbon dioxide woven through dusty ice, water ice deeper down, warming will unlock them in sequence. Early, the supervolatiles punch pathways and loft grains. Later, as grains warm in transit, CN bands flare and atomic nickel lines brighten. If iron requires still higher temperatures or different chemistry to escape, it waits, possibly forever, on this pass. Grain lifetimes seal the case. Millimeter grains can survive long enough to drift thousands of kilometers before fully sublimating, turning the coma into a distributed factory. Smaller grains burn out fast, but are so numerous they create a steady background. Larger clumps behave like slow fuses, delaying their contribution until they've moved well off nucleus. The result is a coma that keeps feeding itself even when the nucleus rotates shadowed faces into view. Continuity without a continuous surface. Source another way, a comet imitates intention. Could a single hyperactive vent fake all this? Sometimes yes, tight jets can dominate a coma, but the breadth of Atlas's green, the superlinear rise across multiple lines, and the sustained water production at distance point to more than one nozzle. This smells like a hybrid, crack-open events on the surface seeding a grain-rich coma that then becomes the main stage. And that hybrid model explains the mood swings. Small temperature, nudges flip big responses, because there are thresholds everywhere in pores, in layers, in grains drifting through sunlight. Switches, cracks, and icy grains don't just decorate the mystery. They are the mystery, translated into mechanics. Next, we'll let trajectory play historian, because the path the comet takes can tell you where its chemistry learned these tricks. Where you're going tells a story about where you've been. 3. Atlas is not bound to our Sunday. Its orbit is hyperbolic eccentricity greater than 1, which means it arrived from interstellar space, dipped a curve around the inner system's gravity, and will leave again forever. That alone sets the tone. This is a visitor, not a citizen, but the precise shape of that hyperbola, stitched together from early and recent detections, can do more than brag about speed. It can point a finger back into the galaxy. Let's talk receipts. Before anyone knew Atlas would be interesting, all sky surveys were quietly photographing the background night after night. Once the comet was flagged, astronomers ran a precovery search combing those archives for earlier, fainter sightings. They found them. Dots of light at larger heliocentric distances, some near 6 astronomical units inbound, each one adding a pin to the map. With every recovered point, orbital elements tighten, perihelion timing, inclination, node, asymptotic velocity. The error bars shrink, the past gets less foggy. Now bring in Gaia, the star-mapping juggernaut. Gaia doesn't observe comets, but it does hand us a 3D atlas of where stars are and how they move, with exquisite precision. Combine Atlas's refined inbound direction and speed with Gaia's stellar motions, and you can run the tape backwards, numerically integrating the comet's trajectory through a changing gravitational landscape. You ask a concrete question: what neighborhoods could launch an object that, millions of years later, intersects our solar system with this exact approach vector and velocity? The answer isn't a street address. Galactic pinball is messy, passing stars, spiral arm tides, and molecular clouds all tug trajectories over long times. But you can still color in a region on the map, and here's where it turns delicious. The vector and speed Atlas carries look more at home with the Milky Way's thick disk population than with the thin disk where our sun resides. Thick disk stars are older, swim higher above and below the galactic plane, and typically have lower metallicity, astronomy speak for fewer heavy elements like iron and nickel relative to hydrogen. If Atlas was born in that crowd, it grew up in a chemical pantry different from ours. Suddenly, the weird pieces we've been juggling sit on the same table. Nickel that walks without iron, an apparent tilt toward carbon dioxide in the volatile budget, early water activity assisted by microstructure and grains. None of those require magic. They can arise naturally if the natal disk was seasoned by a different blend of supernova yields, if the dust-to-ice ratio and condensation sequence ran on a slightly altered clock, if irradiation histories sculpted ices in a distinct way. Change the cosmic upbringing, and you change the rules of engagement when sunlight arrives. Of course, humility is part of the game. Backtracing an interstellar object for tens of millions of years is like trying to reconstruct a river's source from ripples near the delta. Small uncertainties compound. One stellar encounter you didn't model just right can nudge the path by a hair that becomes a gulf given time. That's why the claim is framed as likelihood, not identity. Atlas probably hails from older, lower metallicity territory. It probably didn't learn its chemistry in a nursery like ours, but probably is powerful when it lines up with independent clues. If a thick disk origin is plausible, nickel-iron decoupling looks less like a glitch and more like a signature. If a lower metallicity environments imprint different ice stacks, a carbon dioxide forward comet stops being an outlier and starts being a data point on a trend we haven't graphed yet. The orbit, in other words, doesn't just tell us where Atlas is going, it whispers when and where its rules were written. Here's the dramatic turn. If 3I Atlas is a fossil from an older galactic epoch, then every spectrum we take is a core sample from a time before the Sun existed. We're not just watching a comet pass through. We're reading history in motion, the chemistry of another era, delivered to our doorstep by a path only gravity could write. Next, we trace that chemistry back to its factory floor, supernova recipes, and elemental barcodes that might explain why nickel is loud while iron stays quiet. What if 3I Atlas isn't just a weird rock, but a tag from a distant factory, its chemistry stamped with the signature of the explosions that seeded its birth cloud? Stars build the periodic table in stages. Low-mass stars fuse gently for eons. Massive stars fuse furiously, then die spectacularly as core collapse supernovae, launching a storm of newly forged elements. White dwarfs in tight binaries can also detonate. Type 1, a supernovae adding another, different chemical recipe to the mix. The galaxy's gas is a stew of these yields, and every future star and planetesimal inherits the blend. Nickel and iron are cousins in that story, but they're not twins. Core collapse supernovae and Type 1a events produce different nickel to iron yields depending on details like progenitor mass, metallicity, and how the detonation unfolds. Over billions of years, regions of the Milky Way sample different mixes of those events. The thin disk where the Sun lives has been seasoned by many recent supernovae, including a healthy dose of Type 1a explosions that are prolific iron factories. The thick disk, older, puffier, more kinematically hot, locked in a different balance, earlier in the galaxy's life, with yields and ratios that don't precisely match ours. If 3I Atlas condensed out of solids in a thick disk protoplanetary disk, its mineral pantry would reflect that older chemistry. That doesn't mean more nickel than iron in bulk. It could mean nickel was incorporated into phases that nature frees easily under gentle warming, while iron was preferentially locked into tougher, more refractory grains. When sunlight starts to work the surface and coma, the nickel atoms slip the leash first, lighting up their spectral line. Iron, caged more tightly, stays dark until higher temperatures or different pathways unlock it temperatures this comet may never reach on its brief visit. That's the observational trap and the opportunity. Spectra tell you what's in the gas now, not the true inventory underground. Emission lines are like receipts for the easiest to spend cash, but patterns across many comets can still reveal the vault. If we see nickel-bright, iron-shy emissions recur in objects with similar inbound kinematics and halo-like or thick disk approach vectors, we start to suspect a shared origin. Suddenly, the missing iron is less about an individual's quirk and more about a population's birth certificate. Elemental ratios aren't the only barcodes. Isotopes variants of the same element, with different neutron counts, carry even more precise history. Oxygen and carbon isotopes have already proven their worth in tracing solar system reservoirs. Nickel isotopes could, in principle, do the same for interstellar visitors, flagging the balance of supernova types that enrich their natal clouds. We probably won't get that granularity from remote spectra soon, but it's a North Star for future intercept missions. A tiny lab sniffing atoms up close could read the digits on the galactic barcode. There's a reasonable alternative we can't ignore. Surface processing might bias everything we see. Eons of cosmic rays and ultraviolet light could build a veneer where nickel is enriched or iron is chemically immobilized. In that case, the nickel line is a story about the last billion years of exposure, not the first few million years of formation, but even then, population studies help. If space weathering alone explains it, we should find similar nickel-iron quirks across objects with wildly different trajectories. If the quirk clusters with certain orbits and speeds, the sort associated with older galactic components' origin creeps back into the frame. This is the dramatic promise, a comet as a tracer particle for galactic archaeology. Astrophysicists already map the Milky Way by reading the chemistry of stars. Interstellar ices and rocks are the unsung complement solid-state samples of the same history, wandering into our laboratory by grace of gravity. Each unusual ratio, each stubborn line that appears without its partner, is potentially a breadcrumb, pointing to a birthplace with a different supernova diet. If nickel in 3I Atlas is a barcode, then the next logical step is obvious. We don't just stare at one tag, we build a catalogue. We treat every interstellar visitor as a volume in a sprawling library and start shelving them by chemistry, orbit, and epoch until the galaxy's filing system reveals itself. Imagine the galaxy as a library and interstellar objects as books that got lost in the mail. Every so often, one lands on our doorstep with a cover we don't recognize and a language we barely speak. Oumuamua, Borisov, Atlas, 3 volumes shelved side by side, already suggest the catalogue is wilder than our local section. So what would it look like to stop reading ad hoc and start building an index? First, we decide what belongs on the spine. For each visitor, we log trajectory parameters, approach vector, asymptotic speed, inclination relative to the galactic plane. That's our geography. Then we attach a chemical table of contents, volatile ratios across, distance, metal lines and their timing, dust to gas behavior, color evolution, any evidence of distributed coma sources like lifted icy grains. If we're lucky, we add isotopic hints or polarization signatures that trace grain size and structure. Not every entry will be complete. That's fine. Libraries grow by fragments. Second, we link shelves. Objects with thick disk-style kinematics get grouped, even if their chemistry isn't a perfect match. Thin disk travelers form another cluster. If we're right that environment imprints composition, patterns should emerge. Maybe thick disk objects trend toward carbon dioxide-forward volatiles and nickel-first metals. Maybe thin disk visitors look more like our comets water-heavy nearer the sun, iron and nickel appearing together as temperatures climb. Outliers won't break the system. They'll flag subshelves worth investigating. Third, we handle time. A comet's spectrum is not a static text, it's a serial with episodes. Early inbound might show only CO-driven stirrings. Mid-course, the coma turns into a factory as grains wake. Near perihelion, refractory species crack loose or remain stubborn. By archiving sequences how each line rises and falls with solar distance, we're effectively videotaping the chemistry. 2 comets with similar inventories can still tell different stories if their thresholds and switches trip at different moments. That timing is a fingerprint. Fourth, we scale the reading club. Big surveys, Rubins scanning the optical sky, radio arrays tracing diffuse structures, UV-IR instruments in space become our acquisition system. Citizen observers feed the margins with light curves, colors, and serendipitous catches when professional telescopes are weathered out or overbooked. The goal is ruthless coverage. Don't miss the early chapters. Don't forget the epilogue on the way out. Where does this go beyond pretty plots? Toward a map. If chemistry clusters by approach, vector and speed, we can trace back not to single stars but to galactic neighborhoods, spiral arm segments, thick disk strata, halo streams. If volatile stacks correlate with likely stellar metallicity, we start to connect solid-state chemistry to the stellar abundance patterns astronomers already use. In other words, interstellar comets become moving ground truth for galactic chemical evolution models that, until now, leaned almost entirely on starlight. There's a deeper payoff too. Diversity measured is diversity explained. Once we have 50 or 100 well-characterized objects, we can invert the problem. Given a set of volatile ratios and activation thresholds, predict what kinematics the object should have if it came from the thick disk versus the thin disk. Given a metal emission sequence, forecast whether iron will ever join nickel before perihelion. Miss on those predictions and you've found physics you didn't know you were missing. Hit, and you've validated a story about how star systems write their comets. And what about the human part? Libraries teach patience. You don't skim every page at once. You annotate, cross-reference, and return when you've learned a new language. Atlas is one book, yes, but it's also a prompt to build the shelves we'll need when the deliveries start arriving monthly. The galaxy is already sending us a curriculum. Our job is to stop treating each object as a one-off miracle and start reading them as chapters in a coherent, unbelievably rich textbook. Which brings us to a cautionary chapter we can't skip: how to separate meaningful connections from coincidences that only look like design. 2 bright dots headline the same month. Mercury climbs into a friendly evening apparition. Ceres swings to opposition, big and photogenic. Meanwhile, an interstellar comet starts acting alive. Put those 3 on the same calendar, and the brain starts sketching lines between them, Alignment, influence, a hidden rhythm in the sky. It feels persuasive because it feels tidy, but the universe isn't obliged to our aesthetics. Let's do the unromantic math. Mercury is small, just over a third of Earth's diameter, and it orbits close to the Sunday. Its gravitational pull on a body far out past Mars is microscopic. Ceres is even smaller and farther away. Stack their gravity fields together, and you still can't budge an interstellar comet's outgassing, which is governed by local sunlight, material properties, and vacuum pathways. The forces simply don't reach. That's not a vibe check. That's orders of magnitude. So why does the pattern seduce us? Because we're built to see faces in clouds and tigers in grass. Evolution favors false positives. Better to jump at an illusion than miss a real predator. Transfer that wiring to the night sky, and you get cosmic pareidolia coincidences promoted to conspiracies. We remember the alignments that bracket a strange event, and forget the hundreds that didn't. The hit sticks. The misses evaporate. History has a loud case study. In 1910, Halley's Comet returned, and astronomers found cyanogen in its tail. Newspapers splashed headlines that Earth would pass through poison. People bought gas masks and sealed their windows. The actual physics? The tail is thinner than any vacuum chamber. Even if cyanogen drifted through the atmosphere, the quantities were undetectably small. But timing, plus a scary word, equals panic. It took years for the public to unlearn that reflex. Now translate that lesson forward. Mercury looking great in the west says nothing about Three-Eye Atlas flipping switches millions of kilometers away. Ceres shining at opposition is Earth geometry, not a cosmic command. The only honest bridges are the ones engineered by forces that scale across those distances. And here, those bridges don't exist. Sunlight, yes. Gravity from the sun and huge planets, yes. Tiny inner worlds tugging on a distant interstellar visitor's chemistry? No. There's a more subtle trap. When multiple unusual stories share a news cycle, say, a green comet and a hush around a commercial suborbital flight, the mind bundles them. The bundle feels like a pattern, and the pattern demands an author. But shared timing on the internet often just means shared attention. Algorithms amplify what's sticky, not what's causally connected. If you don't actively separate coincidence from mechanism, the scroll will do it for you and it will choose drama every time. So how do we keep the wonder and lose the superstition? We ask blunt questions. What force connects A to B? How strong is it at the relevant distance? What's the sign? Does it push the right way? Are there counterexamples when the alignment happened and nothing followed, or when the effect happened without the alignment? If the link disappears under those tests, it wasn't a link. It was a lyrical arrangement of dates. This isn't a killjoy stance. It's a way to protect the real magic. The true stories of cause, sunlight threading pores, grains waking in the coma, nickel lines rising while iron stays quiet, are more interesting than calendar coincidences because they survive scrutiny. They let us predict the next chapter instead of inventing one after the fact. They turn a sky full of tempting patterns into a laboratory where curiosity can actually win. Keep your awe. Ditch the false chords. The universe has plenty of actual music, and the next movement starts with the people who catch the notes algorithms miss. Some discoveries don't arrive with a trumpet blast. They show up as faint rings in a sea of radio fuzz, and an algorithm shrugs. Then a human stares a little longer and says, "That's weird." Odd radio circles, vast ghostly halos only visible at radio wavelengths were first spotted that way. Not by a machine expecting a tidy point source, but by people trawling maps and flagging the things that didn't fit. That's the power of the crowd. It specializes in the unexpected. Radio surveys like LOFAR paint the sky in low-frequency detail. The scale is hard to grasp. Petabytes of data, millions of compact sources, and in between them, diffuse structures that smear across pixels. Automated pipelines are brilliant at finding dots. They're less brilliant at whispery circles with edges so soft they could be artifacts. Volunteers became the anomaly net. They clicked through tiles, argued in forums, and elevated candidates that no catalogue would have promoted. One flagged object wasn't just an orc, it was the biggest and most powerful yet. Twin rings intersecting in a figure eight. A machine didn't miss it because machines are dumb. It missed it because the training set never taught it that ring-shaped fog matters. Citizen science isn't magic, it's a scaling strategy. When data arrives faster than experts can look, you hire the planet. You give people clean interfaces, short tutorials, and examples of both true positives and seductive fakes. Then you add guardrails. Multiple independent flags before a candidate rises. Golden set images seeded in the stream to measure accuracy. Leaderboards that reward careful eyes over click-happy noise. By the time a target reaches professionals, the signal-to-noise is high enough to justify scarce telescope time. Does this produce false alarms? Of course. But false alarms are the tuition you pay for not missing the weird. The trick is to keep the rate affordable. Tiered validation helps. So, does mentorship experienced volunteers teaching newcomers what instrumental ghosts look like, how diffraction patterns masquerade as structure, why seams in mosaics can create perfect fake circles? This community expertise is a resource that grows with every project, and it's surprisingly portable. The person who learned to spot a bogus radio ring will be deadly at catching bad galaxy light curves later. Now, plug that into 3i Atlas. Imagine a curated stream of comet spectra and photometry flowing to a trained crowd. Volunteers don't need PhDs to spot a nickel line that rises without its iron partner, or a color curve that turns green too fast to be geometry. They flag anomalies. Professionals swoop in with bigger gear. A week saved early is the difference between catching a threshold flip inbound and missing it until the show is half over. With interstellar visitors, time is the scarcest commodity. Amateurs buy it back. There's a hard boundary we respect. Discovery claims aren't official until they survive cross-checks, calibration, and peer review. Citizen science doesn't replace that discipline. It feeds it. The pipeline from "hey, that's odd" to "here's the paper" gets shorter, and the bias toward what algorithms already expect gets weaker. That's healthy science. And let's not ignore the emotional dividend. When people see their click turn into a telescope on target, curiosity becomes ownership. The sky stops being distant content and starts being a place you can help read. That feeling is rocket fuel for education, for careers, for the patience to stick with a mystery when the first explanation falls apart. Machines are getting better. They'll learn rings, and green comet, and nickel-first spectra. Then the universe will throw something sideways again, and we'll need the crowd's eyes. That's the game. That's the partnership. Algorithms harvest the obvious. Humans catch ghosts. Together, we keep the net tight enough that when the next message crosses the dark, it doesn't slip through. 6 humans ride a rocket above the Kármán line and the internet yawns. That shouldn't happen. Suborbital flights are built for spectacle. Wide cabin windows, slow spins, smiling passengers, the blue earth rolling beneath. Usually, the clips are everywhere within hours. This time, the story arrived and then slipped between the algorithmic gears. Silence, where a highlight reel should be. Start with expectations. We expect a clean arc of coverage, pre-flight hype, launch day live streams, cabin cutaways, landing celebrations, post-flight interviews. We expect a glossy sizzle reel within 24 hours. We expect snappy edits saturating feeds, reaction duets, memes of hats floating in microgravity. When that arc is incomplete or oddly delayed, the absence becomes a presence. The brain treats missing footage like negative space in a painting. Your attention drifts to the gap and wonders why it's there. There are boring explanations, licensing delays, a comms team juggling multiple embargoes, a payload customer who requested privacy and shaped what could be shown, a production hiccup that ate the best angle. Even a launch that was so routine it failed the novelty test. Routine is bad for the scroll. Algorithms reward surprise. If the launch felt like déjà vu to the recommendation engine, it will bury it under something hotter. That silence is cultural more than conspiratorial. But silence is flammable when paired with a crowd trained by past drama. A few months earlier, a celebrity flight became a forensic battlefield as viewers scrutinized hair behavior in microgravity, hatch latches, window reflections, even the gloss on gloves. Once a conversation gets that granular, it sets a baseline expectation. Proof must be immaculate, or doubt will fill the vacuum. When a later mission offers fewer angles and quieter coverage, it reads like a retreat even if the reasons are mundane. Here's the dangerous pivot, linking unrelated anomalies. A green interstellar comet lights up the sky. A suborbital company goes quiet on B-roll. The mind draws a line, because it loves lines. That's how conspiracies get aesthetic momentum. They feel symmetrical. It's satisfying to imagine a hidden narrative tying spaceflight publicity to cosmic weirdness, as if the universe was staging an act and the media was handed a script with missing pages. It's satisfying, and almost certainly wrong. So how do we navigate the gap without tumbling into it? We ask what evidence would move us. Clear timestamps tied to telemetry, multiple camera angles that agree, third-party trackers confirming ascent and descent profiles, independent observers near the range reporting the crack of the booster. We write a checklist that doesn't assume guilt or sainthood, and we apply it consistently to every flight, not just the ones that feel uncanny. Meanwhile, we tolerate the possibility that this mission just wasn't built to be a content machine. Not every rocket carries a cinematographer. There's a lesson for science communication buried in the dust. If you don't publish the receipts that audiences now expect, someone else will publish a story. Attention abhors a vacuum. The fix is transparency. That's boring in a way only engineers can love. Timestamps, telemetry overlays, slow cuts that prioritize context over hype. The internet won't always reward that. But the people who matter, the ones who stick around after the fireworks, will. And there's a lesson for us too. Keep your curiosity sharp, not brittle. Curious says, I want more data. Brittle says, the lack of my preferred footage equals fraud. One grants you patience, the other steals it. When a real anomaly arrives like a comet painting the sky green with Nichols singing solo, you'll want your patience intact. You'll want to save your skepticism for the claims that can't survive it. The silence was weird. Weird isn't proof. As with 3i Atlas, we hold two thoughts. Keep asking, and keep checking which questions actually point to forces that can answer. Here's the tightrope. Stay excited without getting fooled. The universe is generous with anomalies, fast radio bursts that crackle for milliseconds from distant galaxies, a star that dims like it's wearing mismatched curtains, a cigar-shaped rock that swerves shyly as it exits the stage, a green comet that flips on like a light. The temptation is to shout revolution every time. The risk is that you burn trust by crying wolf, and the real wolves stop getting invitations. So, how do we do this right? Start by loving uncertainty out loud. Not as a hedge, but as a feature. When Tabby's star baffled observers with irregular deep dips in brightness, the headlines lunged for alien megastructures because it made a perfect thumbnail. Data moved slower. Follow-up observations found wavelength-dependent, dimming dust, not giant solar panels, while long-term monitoring revealed a messy, evolving system that still isn't fully explained. Was the alien angle baseless? No, just premature and unanchored to a predictive test. Wonder survived. Hype didn't. Next, ask for predictions that can lose. A good hypothesis writes checks in public. For 3i Atlas, we can commit to clean markers. If ion lines emerge as perihelion heat rises, then nickel first was timing. If they don't, then metal decoupling is structural. If carbon dioxide dominance fades close in, then the inversion was a distance effect. If it persists, the chemistry is genuinely inverted. These aren't vibes. They're forks in the road with signs we can read. Then, build narratives that update. People will forgive a plot twist if you foreshadow the possibility. Tell them which alternative endings are on the table. Say, here's where the story gets really strange, or it snaps back to normal in a way that teaches us more than the drama would have. Treat viewers as collaborators, not customers. When new spectra arrive, revisit earlier claims and move the goalposts in daylight. The thrill isn't in being right on the first draft, it's in watching reality correct the draft. We should also police our metaphors. Calling a comet alive is fine poetry. Pretending it implies biology is a bridge too far. Actionable translation helps. Alive means thresholds and feedback loops, valves and vents, not cells and genes. If you can swap the metaphor for a mechanism without losing the beat, you're communicating. If the beat dies without the metaphor, you're charming yourself, not teaching. On the media side, resist the algorithm's hunger for certainty. It rewards maximal claims, the most baffled scientists, the most impossible object, the most paradigm-breaking discovery. You can hack that psychology without lying, frame the real stakes. Say what rules would bend and what would break under each outcome. The audience can handle conditional excitement. In fact, it's more addictive because it pays off over time. They'll come back to see which door the data kicked open. There's also a craft answer: rhythm. Drop fast, punchy explanations between the big swells of awe. Keep sentences short when the concepts go tall. Visuals that ground scale 40 kilograms per second equals a small car's mass every minute anchor the fireworks in something you can feel. Hype is empty sugar. Rhythm is protein. It feeds attention without crashing it. And when we do get it wrong, we say so, not with a sigh, but with a grin. The universe outsmarted us. Great. Now we're smarter. The correction becomes part of the story arc, not an apology tacked on at the end. That attitude keeps curiosity elastic instead of brittle. Wonder without hype isn't less thrilling. It's more durable. It lets a green comet be dramatic as physics, not as fantasy. It buys trust, so that when you finally whisper the big word discovery, people lean in instead of rolling their eyes. And that trust is the only currency that can carry us through the next anomaly, and the one after that actually changes everything. If carbon dioxide is calling the shots in 3I Atlas, then its nursery probably ran warm and weird. Comets inherit the climates of their birth disks. Move the condensation fronts the invisible lines where different ices can solidify, and you change the pantry. Water freezes farther out, carbon dioxide a bit. Closer in, carbon monoxide even farther out in the deep freeze. Shuffle those lines with stellar radiation, turbulence, and migrating planets, and you stamp very different recipes into the rocks that will one day go wandering between stars. Picture a young star wrapped in a sprawling, dusty disk. The inner regions glow hot, the outer mist glows cold, and in between sits a turbulent mixing layer where pebbles and ices collide, stick, and trade coats. If giant planets form early and migrate, they plow pressure ridges through the disk, trapping drifting grains and hauling volatile-rich material inward. A pebble that started life beyond the carbon monoxide snowline can get parked near the carbon dioxide snowline, then accrete layers of dust and organics while keeping its carbon dioxide bounty. Assemble enough of those pebbles into a comet embryo, and you've built a future carbon dioxide-forward traveler. Now, add irradiation. The kind of star matters. Hotter, bluer stars blast disks with more ultraviolet light, cooking ices and reshuffling chemistry on grain surfaces. Even around sun-like stars, flares and accretion bursts can temporarily spike the radiation field, driving reactions that bank carbon dioxide in fragile matrices. Cosmic rays thread it all, splitting bonds, making and unmaking molecules that will later dictate which lines light up when sunlight returns. Over millions of years, that processing can bias what gets liberated early and what stays locked until the heat is truly on. This is where 3I Atlas starts to look like a postcard from a slightly warmer shelf. A disk where carbon dioxide was easy to incorporate. A migration story that dragged carbon dioxide-rich pebbles inward without stripping them bare. A radiation history that left water present, but less dominant in the layers most ready to vent at distance. When 3I Atlas sails into our sunlight, the first volunteers are the super volatiles and carbon dioxide. They punch vents, loft grains, and jumpstart the coma factory. Water shows up in the receipts earlier than we'd expect, thanks to microclimates and grain sublimation. Then the green arrives, cyanide and nickel turning the color dial as thresholds are crossed. The sequence reads like a thermal table of contents written long before the comet ever met our sky. Could you build the same outcome without a warm birthplace? Possibly, if the nucleus is layered like an onion. Imagine carbon dioxide-rich strata near voids, or crack networks that present low activation barriers, while water ice hides deeper behind dust mantles. Thermal fracturing would expose carbon dioxide first, then set the stage for water and later species. But that geometry begs the earlier question: why did the layers arrange themselves that way? Birth environment keeps tugging on the thread. There's a tell we can chase. If carbon dioxide-forward comets tend to come in on thick disk-like approach vectors, we've got a population link between chemistry and kinematics. If they don't, and carbon dioxide dominance pops up across a mishmash of trajectories, then the pathway is more universal disk physics that can recur in many neighborhoods. Either answer elevates the story. The first maps chemistry to galactic era, the second maps it to common disk mechanics. Practically, carbon dioxide worlds change how we hunt. We bias surveys to catch the faint breath of super volatiles at distance. We treat a lack of early water lines as ambivalence, not absence. We expect grain factories to dominate early and plan instruments to watch color curves, not just flux. And when a green coma blooms, we don't gasp at magic. We check the boxes: early carbon dioxide pressure, grain lift, threshold timing, nickel singing solo or joined by iron. Warm birthplaces don't make comets alive. They make them theatrical. They preload the stage with props layers, volatiles, fragile compounds, so that a few watts of extra sunlight can trigger a whole act. 3. iAtlas is performing a script it learned long before it reached us. Our job is to reverse engineer the playwright, the disk, the star, the radiation, and the migrations that taught a chunk of ancient ice to turn green and argue with iron. Tiny temperature changes can unlock huge chemical tantrums. That's the headline. At 3.5 astronomical units, the numbers look stingy. Sunlight is weak, equilibrium temperatures hover around 150 Kelvin, but materials don't respond linearly to heat. They respond in cliffs. Cross a cliff, and a quiet surface becomes a vent becomes a jet becomes a factory. Start with activation energy, the toll you pay to turn solid molecules into gas. For water ice embedded in dusty porous matrices, the toll is high. For supervolatiles like carbon monoxide and carbon dioxide, it's lower. But even lower doesn't mean gradual. In a porous medium, heat doesn't spread evenly. It channels along contacts, collects in cul-de-sacs, and stalls in shadowed throats. A shallow pit with the right geometry can trap radiation and re-radiate it inward, adding a few Kelvin where it counts. Those few Kelvin push molecules over the cliff. Once the first molecules jump, they drag neighbors with them. Pressure is the second lever. Sublimation in a closed pore raises local gas pressure, which can counteract further sublimation. Crack the pore to vacuum, and the pressure plummets. Now sublimation runs faster, because escaping molecules no longer pile up. This is why microfractures matter so much. A grain boundary that opens by a micrometer changes the thermodynamics of an entire pocket, flipping a process from throttled to free-flowing. The result at scale looks like a heartbeat, long calm, sudden surge. Porosity adds a third lever: surface area. A cubic centimeter of fluffy, fractal ice dust aggregate can hide tens of square centimeters of sublimation front inside it. You're not just heating a visible skin, you're warming a labyrinth of pathways. Increase the temperature a little, and the active surface expands a lot. That's why comets often act alive. They're networks. Networks produce thresholds and cascades, whether you're talking neurons, markets, or ice. Now move off the nucleus and into the coma. Grain lift takes the threshold physics mobile. Tiny ices spun off by the first vents act like sensors with knobs set to just above ambient. As they drift, solar input and radiative cooling fight for control. A tweak in either can flip a grain from storage to release. Thousands flip, then tens of thousands. The gas they release thickens the coma, which increases absorption of sunlight, which warms more grains. Feedback doesn't require intelligence, only coupling. Thermal inertia shapes the rhythm. Materials resist temperature change. When day breaks on a rotating nucleus, the surface lags. The warmest moment arrives after local noon, and the coolest comes after midnight. If cracks and pores sit near thresholds, this lag produces phase-shifted outgassing, jets that hit hardest when the sun is already lowering, or flares that linger into local night because warm interiors keep bleeding heat. To a telescope, those pulses look intentional. To physics, they're inertia plus thresholds playing tag. Dust mantles complicate everything. As gas drags grains outward, some fall back like ash and blanket active terrain. A few millimeters of insulating dust can smother water while still letting carbon dioxide seep through microchannels. Mantles move thresholds upward, demanding more heat for the next surge. But they also store instability. A small slump can expose pristine ice and reset the clock from choke to wide open in a second. Landslides, on a world the size of a mountain, can be measured from millions of kilometers away by nothing more than a spectral line that suddenly blooms. None of this requires new laws. It requires respecting how old laws behave in complex media. 3. iAtlas is a seminar in that respect. Early OH says pockets found vacuum sooner than we thought they could. The green surge says grains crossed their cliffs together. Nickel without iron says some thresholds are reachable and others aren't yet. If iron stays dark at perihelion, the explanation is not magic, is that the necessary cliff lies beyond the thermal path available this passage. This is why small temperature errors in models can produce big predictive failures. You can miss by 3 Kelvin and miss the event entirely. The fix is to model the network, not just the globe. Poor scale heat flow, crack mechanics, grain trajectories, radiative transfer in a semi-opaque coma. Hard, absolutely. But the payoff is a theory that expects the drama instead of being surprised by it. Next, we scale from the physics of one object to the machinery that will find dozens like it. If thresholds make comets theatrical, surveys make theatres everywhere watching, waiting, ready to catch the first line. If interstellar comets are letters, we need a postal service that never sleeps. The plan is already on the launch pad. In Chile, the Rubin Observatory will scan the entire visible sky every few nights with a camera the size of a car, catching anything that moves, brightens, or blinks. In radio, arrays will listen for diffuse structures and molecular whispers. In orbit, ultraviolet and infrared eyes will watch wavelengths Earth's air swallows. Stitch those together, and you get something we've never had before, a sky where surprises have nowhere to hide. Rubin's cadence is the first game changer. Every patch of sky gets revisited on a schedule measured in nights, not months. That means fast movers, interstellar candidates, with high inbound speeds and unusual tracks, stand out like bold strokes on a flipbook. Link a handful of detections, solve for motion, and you can flag not bound to the sun early, while the object is still brightening inbound. Early is everything. It buys time for a spectroscopy before the show peels away into the dark. Next comes triage. A global network of medium telescopes turns those candidates into facts, colors, basic spectra, first hints of activity. If lines pop carbon monoxide in the cold, carbon dioxide in the mid-cold, OH shouting water, you escalate. Big mirrors swing. High-resolution spectrographs lock in, and polarimeters measure how light scatters off dust to estimate grain sizes. Meanwhile, small scopes swarm the light curve, looking for outbursts, rotation, and the mood swings that mark threshold physics. This is a relay race where every baton pass shaves hours, and hours decide which chemistry we catch. In radio, sensitivity to low surface brightness structures means we won't miss the foggy stuff our optical algorithms ignore. If an interstellar visitor drags a broad, faint halo of gas or lights up a rare molecule, radio arrays will flag it. UV and IR from space finish the spectrum, accessing forbidden bands and clean carbon dioxide windows. The point isn't just redundancy, it's synthesis. One wavelength tells you what, another tells you where, and how fast. Together, they tell you why. Automation helps, but humans stay in the loop. Alert brokers' software that filters millions of nightly detections will score each candidate on weirdness. But we still need the crowd and the pros to sanity check. A comet with a color curve that greens too early. A spectrum where nickel rises without iron. A light curve that pulses off phase with illumination. These are the flags a trained eye can raise before the big guns roll, turning what might have been a missed beat into a recorded verse. All this infrastructure changes our psychology too. Instead of waiting for a miracle, we plan for a stream. Monthly interstellar candidates is not science fiction in the Rubin era. Some will be boring in precisely the way we need anchors for what's average. Some will be loud. A few will be so strange that our models cough. That distribution is the goal. You can't map diversity with a handful of postcards. The logistics matter. Standardized data formats mean spectra from one telescope drop cleanly into models built for another. Public archives mean a grad student 3 years from now can reread today's lines with a better theory. Rapid target of opportunity protocols mean you don't lose a week to paperwork while a comet crosses the threshold you've waited for. The culture shifts from hope we catch it to we will catch it. Here's how. And then there's the dream version, predictive scouting. With enough detections, you start to forecast. A candidate with thick disk kinematics and a red then green color evolution gets an automatic nickel watch. Another with early carbon monoxide and sluggish OH gets tagged grain factory likely. We stop reacting and start anticipating, staging instruments for the right moment instead of the available one. Scale doesn't kill wonder, it makes wonder reliable. The more we watch, the more we learn to expect the unexpected, and to be ready when an object like 3i Atlas enters the frame. because the next logical question isn't just whether we'll see it. It's whether we'll meet it up close. Seeing is good, touching is better. If interstellar comets are letters, the dream is to open one in our hands. The problem is speed. Visitors like 3I Atlas cross the inner solar system in months, moving tens of kilometers per second. By the time we notice, they're already halfway to goodbye. Catching one requires a different mindset. Launch-ready hardware, fast propulsion, and a mission plan that treats calendars as enemies. There are two broad plays. The first is launch on alert. Park a small, agile spacecraft on Earth, or better, in high orbit. Keep it fueled, and when an inbound interstellar object is flagged, sprint. The checklist is brutal. Rapid trajectory design, an available booster with enough kick, and a spacecraft with a propulsion stage that can add several kilometers per second after separation. Solar electric propulsion, efficient but slow, won't cut it alone for rendezvous. You need chemical burns or solar thermal stages to pour on delta V quickly, then maybe ion engines to trim the match as you coast in. The second play is pre-deploy. Station a scout away from Earth at an inner solar system way station, like Sun-Earth, L1, L2, or even in a heliocentric orbit slightly inside Earth's. Give it high ISP propulsion, large solar arrays, and an autonomy stack that can accept an update and pivot its target list in days. When the alert comes, the scout is already moving fast in roughly the right neighborhood. The distance to the intercept shrinks, and the required velocity change drops into the realm of the possible. What do we carry when we finally pull alongside? A minimalist lab, a high-resolution mass spectrometer to read volatiles and trace organics, a laser desorption instrument or micro-GC to probe complex molecules, a dust analyzer to weigh and size grains, and a compact camera suite with polarimetry to infer structure. Add a micro-impactor or harpoon to kick up subsurface material for a fly-through sniff, because surfaces lie and fresh ejecta don't. If the budget is bolder, include a sample capsule with an Earth return trajectory. A gram of interstellar regolith in a clean lab is worth more than gold. It's time travel in powder form. Matching velocity is the money move. A flyby at 15 kilometers per second yields gorgeous pictures and frustrating chemistry, because dwell time is measured in minutes. Rendezvous buys you hours to weeks' time to watch thresholds flip as the object warms, time to see whether iron ever rises to join nickel, time to track the coma's grain factory as it evolves. But rendezvous costs. Every meter per second you need late is a meter per second. You should have bought early with a better staging orbit, a hotter upper stage, or a braver launch window. Autonomy is not optional. Communications, light time, and the pace of unfolding events demand onboard targeting and adaptive exposure control. The spacecraft must change modes as the environment surprises it, flare the spectrometer when a line erupts, widen the camera's dynamic range when sunlight scatters off unexpected dust sheets, back off when particle counts spike. Think of it as a robotic field scientist with a checklist and the permission to deviate when the outcrop looks interesting. This is hard engineering, not fantasy. The pieces exist. Small sats can carry serious labs now. Commercial heavy launchers can throw modest payloads onto aggressive trajectories. Software can fly precision approaches with less hand-holding than ever. What's missing is the glue. Funding to keep a bus on the shelf, international agreements to reserve rapid launch windows, and a standing team that rehearses for a target that doesn't exist yet. Disaster response has strike teams. Planetary science needs one for miracles. Here's the payoff, beyond the headline photos. A close pass would tell us whether nickel's solo act is a surface lie or a bulk truth. It would weigh carbon dioxide against water in situ. It would log isotopes that remote spectra can't resolve: oxygen, carbon, maybe even nickel isotopes that whisper which supernovae spiced the nursery. It would turn speculation into laboratory notes. We won't catch 3I Atlas, but we can be ready for the next messenger. Build the scout, practice the sprint, stock the tiny lab. When the alert pings at 3 a.m., don't post a thread, light the candle and go. We love the idea that weird chemistry means someone was here. A lonely nickel line with iron missing. It's hard not to picture refineries in orbit, factories shredding asteroids, waste streams with skewed elemental ratios leaking into space. Could 3I Atlas be carrying the slag of an industry older than our sun? That's a thrilling question. It's also a trap if we dip to ask it the wrong way. Start with what a technosignature is supposed to be, an imprint of technology that nature struggles to fake. radio beacons with narrowband drift, laser flashes with unnatural repetition, waste heat with the spectral shape of engineered power. In the chemical realm, you'd be looking for molecules with no plausible abiotic pathway under the known conditions, or for element and isotope ratios that scream selective processing. Nickel first, iron shy could be the beginning of such a signal or the end of a natural story we haven't finished reading. Industry, if it exists, is selective. You extract iron for construction and leave nickel behind, or vice versa for specialized alloys and catalysts. Over time, tailings pile up with lopsided compositions. If those tailings are ground into dust in a debris belt, some fraction could be incorporated into comets that later get ejected between stars. Millions of years on, one of those comets swings by our sun and vents atoms that reveal the skew. It's not a crazy chain, it's just long, and each link has a natural twin. Nature also separates. Fractionation during condensation and metamorphism sorts elements by volatility and bonding. Organometallic complexes can pack nickel into fragile molecules that sunlight snaps easily, freeing atoms at temperatures that still leave iron locked. Space weathering sculpts a veneer that vents nickel first. Every industry could has a chemistry does. That's why the burden of proof is asymmetric. Extraordinary claims need tests that natural processes can't pass by accident. So what would that test look like here? One version is correlation that refuses to go away. If nickel-alone comets cluster by trajectory in ways that map to likely ancient industrial neighborhoods, that's suggestive, but we don't know where to look for such neighborhoods. A stronger version is a bundle of anomalies, nickel without iron, plus an isotope ratio impossible for supernova, yields, or nickel anomalies alongside truly non-natural molecules, like long-lived fluorinated organics with no plausible cold space synthesis, or a thermal signature in the coma that hints at internal power beyond sunlight. One oddity invites poetry. 3 independent oddities start to write prose. Data discipline keeps us honest. Predict before you peak. If the nickel line in 3I Atlas is technological residue, then it should behave like a passive tracer, track with total outgassing in simple proportion, appear wherever venting appears, and show no activation threshold tied to specific temperatures. If it's chemistry, it will care about thresholds, lag, or lead other volatiles, and perhaps anti-correlate with dust in ways that reflect how grains are processed. That's a test we can run with time series spectra and coma maps. There's also culture to manage. Technosignatures are catnip for thumbnails. If we let drama set the bar, we'll burn the very trust we need when a real signal arrives. The better posture is hungry skepticism. Ask the fun question, then build the unfun checklist. Abiotic pathways canvassed, lab spectra matched, instrument systematics beaten down, predictions scored in daylight. If the anomaly survives that gauntlet, excitement becomes earned, not inflated. If industry once existed around some ancient star, it might indeed have left dust in its wake. That dust might ride comets that wander for billions of years. One of those comets might pass our door and spit a signature into our spectrographs. That's a gorgeous narrative. But gorgeous isn't evidence. Evidence is a pattern that nature can't counterfeit, and that we can't explain away with better chemistry. Keep the question, cage the conclusion. Let 3I Atlas teach us the baseline so that, if a future visitor hums a tune no chemistry can sing, we'll hear it and we'll deserve it. Strange lights make honest brains do weird things. That's not an insult. It's an operating manual. We are pattern machines, tuned by survival to connect dots quickly and forgive ourselves for being wrong later. In a forest, that pays. In a sky packed with noise, it can turn curiosity into certainty long before the evidence arrives. Pareidolia is the first gremlin. Show a face-detecting brain enough random texture, and it will salute a face. Upgrade the texture to a noisy light curve or a blotchy radio map, and it will salute a pattern. That's why irregular dips around a star feel engineered, and why a green coma feels intentional. Our minds smooth the jagged edges and write motives on the curve. It's a feature everywhere except science, where the curve doesn't care how you feel about it. Confirmation bias is the second. Once you lean toward an answer, you start noticing only the clues that keep you leaning. A rumor of nickel without iron makes every spectrum look like validation. A theory about planetary alignments makes every alignment look guilty. Meanwhile, counterexamples slide off like rain. The cure isn't shame, it's structure. You pre-register which outcomes would change your mind, and you say them out loud. If iron appears by perihelion, I will update toward timing. If it doesn't, I will update toward structure. Set the trap for your own bias before the data arrives. Then comes motivated reasoning, which is confirmation bias with purpose. You want a world to be true aliens, cover-ups, cosmic patterns that make the universe feel scripted, so you build an argument at the speed of feeling. The internet is a multiplier for this. Algorithms reward engagement, and nothing engages like a tribe defending a narrative. Every new image gets treated as a chess move. The game is fun, the scoreboard is wrong. So how do we protect curiosity from the parts of us that misuse it? We carry a small toolkit. Ask the force question. What mechanism could connect A to B across the distances and energies involved? If none exists, the pattern is aesthetic, not causal. Ask the falsifier. What would I need to see to abandon my favorite explanation? Write it down before you scroll. Ask the base rate. How often do objects like this do things like that without the special cause I'm proposing? If the answer is pretty often, your special cause is probably just decoration. Use ensemble thinking. 1 spectrum is flirty. 10 spectra are a relationship. A single green image can be an artifact or a quirk of processing. A timeline of greening across instruments is a story. A one-off nickel line feels like poetry. A time series that shows nickel rising while iron stays flat. Across changing illumination feels like prose. The difference between poetry and prose, in this context, is predictability. Practice emotional pacing. It's fine to feel the thrill when a graph wiggles where it shouldn't. Let yourself have it. Then schedule an update window days later, when the dopamine has drained and the follow-up data has landed. Curiosity that pauses is stronger than curiosity that sprints. And recognize the social angle. Skepticism is contagious when it's kind. If you treat the person you're arguing with as a co-investigator rather than an opponent, both of you keep access to your best thinking. The result is fewer goalpost shifts, fewer performative mic drops, and more shared checklists. Science is, at its core, a crowd control problem for ideas. The crowd behaves better when you invite it into the method. None of this dulls wonder. It arms it. With a tidy toolkit, you can look at a green comet and feel both the pulse of mystery and the pleasure of restraint. You can hear nickel sing without inventing a conductor. You can love the story before you know the ending, and still insist that the ending will be chosen by forces, numbers, and thresholds, rather than the parts of your brain that evolve to jump at shadows. We will need that discipline for the finale. The next phase isn't about moods or metaphors, it's about promises the data can keep, and what it would take to admit that this time, the rules themselves have moved. Here's where curiosity becomes a contract. We've told a story with branching futures, and now we lay down markers that decide which branch wins. If the rules are going to bend, they won't do it vaguely. They'll do it at specific lines on a plot, at specific wavelengths in a spectrum, on specific dates as 3I Atlas warms. The edge of the known isn't a fog, it's a boundary we can draw and then cross in public. Start with iron. Nickel has been singing. Iron has been coy. As perihelion approaches, temperature and insulation climb. If iron's absence has been a timing trick, this is when the trick ends. We should see iron lines rise from the noise, lagging nickel but joining it, the way comets in our system do when metals unbind together. If the lines stay flat through peak heating and into the outbound leg, while nickel remains bright, then decoupling survives the hottest stage. That becomes a declaration, not a flirtation. We've met a metal chemistry regime our models don't cover. The update writes itself. Iron shy is not a phase, it's a property. Next, the volatile ledger. We've argued that carbon dioxide may be running the show, with water punching above its weight at distance, thanks to microstructure and grain factories. Nearer the sun, the script usually flips, water dominates and carbon dioxide rides along. If Atlas keeps the inversion near perihelion, the inversion is structural. If water takes over, the inversion was a perspective problem, a function of sampling and geometry. Either way, the curve across heliocentric distance is the story. A ratio that stays flat under changing heat is chemistry calling its own shots. A ratio that crosses over is chemistry surrendering to temperature. Both are interesting. Only one forces us to redraw the family portrait. Then, the switches. Superlinear rises in green lines told us thresholds were flipping CN engines waking, nickel sources releasing. Thresholds aren't one-time fireworks if they're truly rooted in structure. They recur with rotation, day-night forcing, and changing solar angles. We look for repeatability. Does the coma brighten in the same bands at the same rotation phase? Do outbursts track a thermal lag rather than the subsolar point? If yes, this is network physics speaking, pores and grains running schedules set by inertia and geometry. If not, if the surges smear out and refuse to pattern our earlier inference about distributed coma sources gets weaker, and a small set of evolving vents may be enough. We can also draw a line under the grain factory hypothesis. Polarimetry and phase angle studies should tell us whether the coma's particle sizes skew smaller during green surges, as you'd expect if lifted icy grains are sublimating after loft. A shift towards small grains that correlates with the green lines is a receipt. No shift? Then color is less about drifting factories and more about surface sources turning on and off. There's a demographic edge as well. If other inbound interstellar candidates, flagged by their thick disk-style kinematics, show the same nickel-first habit, or early OH at large distances, we stop pretending Atlas is a lone puzzle. A second or third instance turns a curiosity into a class. If they don't, if future visitors look nothing like this, then Atlas is an extreme, and we learn from the edges of a distribution instead of its center. None of this requires certainty in advance. It requires wagers. We say, on this date range, watch this line. If it rises, theory A is ahead. If it doesn't, theory B is. We say, if the carbon dioxide to water curve refuses to roll over near perihelion, we start writing models where carbon dioxide can remain dominant even under stronger sunlight. We say, if polarimetry spikes with the green, grains are guilty. If not, vents take the stand. That's the thrill of the edge. You don't need to chant paradigm shift. You need to post your scorecard and let a comet mark it up. If the marks fall where the old charts say they should, we'll tighten our estimates and move on smarter. If they fall in blank space, we'll draw new axes. Either way, the sky answers, and our job is to hear it clearly enough that the answer changes us. A rock can look like it has a pulse when physics stacks its dominoes just right. That's the lesson 3 Atlas keeps pressing into our hands, water whispering at distance where it shouldn't. A coma blooming green as cyanide and nickel flip their switches. Nickel bright without iron's usual harmony. A volatile budget that might put carbon dioxide in the driver's seat. None of that requires life. All of it requires attention. We've followed the receipts. Hydroxyl halos that cash out to 40 kilograms per second of water at 3.5 AU. Superlinear rises that betray thresholds, not theatrics. Spectra that spotlight nickel, while iron stays backstage. A trajectory that points away from our thin disk neighborhood and toward older, lower metallicity streets, places where supernova diets wrote different ratios into the nursery dust. If a comet looks alive out there, it's because networks of pores, cracks, and drifting grains behave like systems with valves and latches. They pause, they surge, they echo with thermal inertia. That rhythm is not a heartbeat, it's heat and vacuum conducting a choir. Alive, but natural, is not a demotion, it's a precise kind of awe. It asks for mechanisms, offers thresholds, and pays you back with predictions you can win or lose. It lets you say, if iron appears by perihelion, timing fooled us. If it doesn't, composition did. It invites you to watch carbon dioxide either hold its throne or surrender as sunlight climbs. It turns the green not into a miracle but into a map of activation across a cloud of icy grains. It takes mystery and leaves it intact while moving it from fog to contour, and the meaning stretches beyond one visitor. 3 interstellar objects in, we've probably learned more about diversity than we did from decades of arguing over which single comet model was right. Oumuamua taught us that activity can hide without a tail. Borisov tutored us in cold-born chemistry that still looks like home. Atlas performs the threshold ballet out where water is supposed to sit quietly, then dares metals to disobey their usual pairing. Together, they say the galaxy doesn't do one recipe, it runs a test kitchen. That's why the library we imagined matters. If we keep logging approach vectors, volatile sequences, metal lines, polarimetry, and timing, Patterns will harden from anecdotes into trends. Maybe nickel first shows up whenever thick disk kinematics do. Maybe carbon dioxide forward objects carry a telltale grain signature early and a stubborn inversion late. Maybe most of what we'll find in the Rubin era is delightfully boring, and that would be a win too, because averages give outliers their meaning. The point isn't to crown a champion model, it's to build a shelf where each oddity takes its place and teaches the next one how to surprise us. There's a human arc here as well. We learned to separate coincidence from cause, so Mercury's pretty evening didn't steal credit for a distant comet's chemistry. We let citizen eyes amplify weirdness that algorithms weren't trained to love yet. We stared at a quiet media cycle around a rocket flight and chose to ask for receipts instead of reaching for plot twists. We practiced wonder without hype, skepticism without cynicism. That posture is not decoration. It's the only way curiosity survives contact with a universe that's both generous and indifferent. So where does this leave us with 3 Atlas? Right where science likes to live, on a ledge with a view. If iron rises, we update. If it doesn't, we update harder. If carbon dioxide keeps ruling near the sun, we sketch disks that make that outcome reasonable. If the green surges repeat on a thermal lag, we stamp distributed coma factory on the ledger. If they smear out, we rewrite the engine room around vents. We promised to let the comet mark our scorecard. Now we read the marks and accept what they say. Here's the last truth I want you to hold. Natural is wild enough. A time capsule from an older corner of the galaxy just swung through our sky and painted it in colors we had to earn the right to understand. It carried the chemistry of a star we'll never visit, and the memory of explosions that happened before the sun was born. It wrote in photons, we answered in instruments. That conversation, slow, careful, thrilling, is how we become the kind of species that deserves more letters. Keep watching. Keep asking for the force, the falsifier, the base rate. Keep loving the moment a graph refuses to behave and the moment it finally does. Somewhere out there, the next postcard has already been flung. Maybe it's CO-rich and shy. Maybe it's as green as a signal flare. Maybe it hums with a ratio no chemistry should sing. When it arrives, we'll be ready with a library, a playbook, and the patience to let nature be dramatic on its own terms. The sky isn't quiet, it's just speaking in thresholds. We're finally learning the language.